So I was standing in my kitchen this morning, and I'm staring into the silverware drawer.
Okay.
We actually have some real silver in there. And then I looked over at this copper wire I have sitting on the counter,
Ah, right. Copper and silver.
and it just hit me. These two things, they look absolutely nothing alike.
Visually, no.
Ah,
Not at all. You've got that classic reddish sort of warm color from the copper,
yeah,
and then the silver is that cool, shiny gray. It's like night and day.
exactly. But here's the thing. For today's deep dive, I was looking at the research, and chemists basically say these two are like twins, or at least very close siblings.
It's a classic case of not judging a book by its cover, really.
Right. I mean, they're both used for jewelry. They're both fantastic conductors of heat and electricity. You can hammer them into bowls and they won't shatter.
Chemically, they're playing the exact same game.
But then, and this is where the mystery really started for me, I started thinking about zinc.
Okay. The stuff inside a penny.
Right. And it looks almost exactly like silver. It's gray, it's shiny. But if you tried to hammer a ring out of zinc,
It'll just snap. It's brittle.
and it's a terrible conductor compared to copper and silver. So you have copper and silver looking different, but acting the same.
And zinc looking like silver, but acting completely differently.
So that's the question for today. What is the secret rule book that these materials are following? Because it's clearly not about how they look on the outside.
It definitely isn't.
Yeah.
And to answer that, we have to go on a bit of a journey. We really have to peel back the layers of reality.
That sounds a little intimidating.
It can be, but our mission today is just to break it down. We want to find the absolute simplest ingredients of the universe and, figure out why they do what they do.
Okay, so let's start with that copper wire. It feels solid. It looks the same all the way through. If I cut it in half, it's still copper.
Right. And what you're describing there is what scientists call a pure substance.
As opposed to a mixture, I guess.
Exactly. Most things in the world are mixtures. The air you're breathing is a mix of nitrogen, oxygen, other gases. A salad is a mixture.
You can physically separate those things?
You can. But a pure substance, like a piece of pure copper, you can't sift it apart. It's copper all the way down.
And that consistency gives it a kind of fingerprint.
It does. And one of the first fingerprints we look for is density.
Ah, density. I always used to get this mixed up with just plain old weight.
It's a common mistake. It's really about how much stuff is packed into a certain amount of space. Like a brick of styrofoam versus a brick of gold, same size, totally different density.
Got it. And in a lab, you'd measure that with like a beaker of water.
You'd use a graduated cylinder, that tall glass tube, drop the copper in, see how much the water level rises, that's your volume. Then you weigh it, mass divided by volume, that's your density.
And pure copper will always have the same density.
Always. It's a reliable clue,
Oh.
but it's still just a physical clue.
Right. It doesn't tell us what copper is at its most basic level. For that, you have to try and break it down chemically.
Exactly. I have to stop pushing it and start, zapping it.
This reminds me of how people used to think water was an element.
Of course. Earth, air, fire, water. It seems fundamental.
But then someone ran electricity through it.
And it started bubbling. It splits into two different gases, hydrogen and oxygen. So water wasn't the end of the line. It was a compound.
So an element is when you finally hit a wall.
That's the definition.
Yeah.
You hit a wall. No matter what you do to copper heat it, react it, whatever, you cannot get anything simpler than copper. You've found an element.
And there are only 118 of them.
Just 118 known elements.
That number just seems so low. I look around me and I see infinite complexity. Trees, cars, clouds, us.
But it's all just combinations of those 118 things. Think of it like a giant box of Legos.
Okay.
You've got maybe, 100 or so unique types of bricks. But with them, you can build a spaceship, a castle, anything. They look totally different.
But if you smash them apart, you're left with the same basic bricks.
The exact same red 2x4s and blue 1x2s. A diamond is just carbon atoms stacked one way. The graphite in your pencil is the same carbon atom stacked a different way.
That's wild. Okay, let's zoom in further. What's the absolute smallest piece of copper possible?
That would be the atom. An atom is the smallest possible unit of an element that still has the, let's call it the personality of that element.
I like that personality.
Because if you slice a copper atom in half, you don't get two smaller bits of copper. You just have subatomic debris. The copperness is gone.
And an atom of iron from a meteorite is identical to an atom of iron in my blood.
Absolutely identical. The universe uses standardized parts. It's incredibly efficient.
We have to talk about the scale here, though, because the word small does not do it justice.
No. It really doesn't. It's almost impossible to comprehend.
The reading had this one analogy that it blew my mind.
Let's hear it.
Okay, so imagine you could expand all of matter. You blow it up until a single atom is just barely big enough for you to see, like a tiny speck of dust.
Okay, so one atom is one speck of dust.
In that reality, if one atom is a speck of dust, your own body would stretch from Philadelphia, Pennsylvania, all the way to Miami, Florida.
Wait, say that again?
From Philly to Miami, over 1,000 miles long.
Wow. That's how many atoms are packed inside us.
Trillions and trillions. And here's the part that's even crazier.
Go on.
Those atoms, they're mostly empty space.
Yes. This is the one that really gets people. The table you're leaning on feels solid, right?
Yeah, feels pretty solid to me.
But it isn't. If you take that atom and you imagine its nucleus, the heavy part in the middle is a marble on the 50-yard line of a football stadium.
Okay, a marble in the middle of a field.
The electrons would be like tiny gnats buzzing around the absolute highest seats in the stands.
And everything in between is.
Nothing. Empty space.
Then why doesn't my hand just go right through the table?
Force fields. Seriously. The electrons in your hand are repelling the electrons in the table. You're not actually touching it. You're floating on a microscopic cushion of electromagnetic force.
That is slightly unsettling and also very, very cool. Okay, so we have 118 types of atoms. Before we had a system to organize them, this must have just been chaos for scientists.
Absolute chaos. You find gold, it's shiny. You find sodium, it explodes in water. You find argon, it does nothing at all. There was no rhyme or reason to it.
Just a big pile of puzzle pieces with no picture on the box.
And this is where my favorite character in this story comes in, Dmitry Mendeleev.
The Russian chemist with that epic beard.
The very same. So it's 1869. He's trying to make sense of the 60 or so elements they knew about back then. He loved playing cards, solitaire specifically.
So he made element cards.
He literally did. He wrote the name, the weight, the properties of each element on a separate card and just started shuffling them around on his desk, playing a game of chemical solitaire.
Looking for a pattern.
Any pattern. And then he saw it. He realized if you arrange them by their weight, certain properties repeat themselves over and over again at regular intervals.
It was periodic.
Hence the periodic table.
But the coolest part of that story for me is what he didn't have. The gaps in his table.
The gaps, yes. He's laying his cards out, and the pattern says, okay, there should be a metal right here under aluminum that behaves in a certain way.
Yeah.
But nobody had ever discovered it.
Another scientist might have said, well, my pattern must be wrong.
But Mendeleev said, no, my pattern is right. The world is missing an element. He left a blank space. He called it eka-aluminum, and he predicted its properties, its density, its melting point, everything.
And a few years later?
They found it. It was gallium. And its properties matched his predictions almost perfectly. That's the power of the table. It's not just a list. It's a predictive map of reality.
So let's decode that map, because this is what solves our copper and silver mystery. How is it organized?
It's basically a grid. The rows are called periods. As you go across a row, you're just counting up. Hydrogen is 1, helium is 2, lithium is 3, and so on.
But the real magic, the answer to our question, is in the columns.
The groups.
Yeah.
Exactly. Elements that are stacked in the same vertical column belong to the same family.
And this is why copper and silver are twins.
Take a look at the table. Copper is atomic number 29. Silver is 47. They're not even close in weight. But
They're both stacked right on top of each other in group 11.
right there in group 11. And this is the why. It's all about the electrons.
Okay, walk me through that.
Picture the atom like an onion with layers or shells. The inner shells are full of electrons and they're boring. All the action, all of chemistry happens in the outermost shell.
The valence electrons.
Right. Think of that outer shell as the atom's handshake. It's how it greets the world.
And elements in the same column.
Have the exact same handshake. Copper, silver, and gold all have a similar arrangement on their outer edge. They all have one electron that's kind of loose and ready to move.
Ah, and that's why they're such good conductors. Electricity is just moving electrons.
Exactly. That loose electron in their handshake means a current can flow through them super easily.
Okay, that explains the similarity. Now, what about zinc? The odd one out.
Poor zinc.
It's right next door to copper. Copper is 29, zinc is 30. They're neighbors.
But on the table, it falls into the next column over, group 12.
Which means it has a different handshake.
A totally different handshake. Zinc's outer shell is full and stable. It's all zipped up tight. It holds onto its electrons very tightly.
So it can't conduct electricity as well, and it's more brittle.
Right. Because its atoms are locked in a rigid grip. Copper atoms can slide past each other because of those loose electrons, so it's dense. Zinc atoms are held tight, so they snap.
So the table is sorting elements by their electron handshakes. That's a perfect way to think about it.
It's all about that outer edge.
Before we move on, I have to ask about the symbols. Cu for copper, Zn for zinc, those make sense. But gold is Au, silver is Ag, lead is Pb.
Huh, that's just history refusing to go away. Those are their old Latin names.
Give them to me.
Gold is Au for aurum, which meant shining dawn. Silver is Ag for argentum.
And lead, P, what's that one?
That's plumbum.
Plumbum, that sounds weirdly familiar.
Think about the pipes in an old house.
Plumbing.
There you go. The Romans used lead for their water pipes. The person who works on pipes is a plumber, from the Latin word for lead.
That's a fantastic little fact. Hey, did you know your plumber is named after a toxic heavy metal?
Maybe don't lead with the toxic part.
Fair point. So, okay, this table isn't just for explaining why some metals are shiny, right? Do engineers actually use this map to build new things?
Oh, constantly. It's one of the most important tools there is. It lets you solve problems without having to test every single material on Earth.
Can you give me a real-world example?
Sure. Let's talk about something called a thermoacoustic generator.
Sounds like it's from Star Trek.
It's a real device that turns heat into electricity using sound waves. It's very cool, but you need to fill it with a specific gas.
Okay.
Now, you can't just use air because the oxygen in air reacts with things. It causes rust. And with intense heat, it could combust.
So the engineer needs a gas that won't react with anything, no matter how hot it gets?
Exactly. So instead of just guessing, you look at the map. You go all the way to the far right to group 18.
The noble gases.
The noble gases.
Helium.
Neon, argon.
And they're noble because they're snobs.
Chemically, yes. Their handshake, their outer electron shell, is perfectly full. They have zero interest in reacting with the commoner elements. They are completely inert.
So you just pick one from that column, fill the machine, and it works.
And it works perfectly. The table turned a chaotic search into a simple menu selection.
It's amazing that this grid, which I'll be honest, terrified me in 8th grade science, is really a cheat sheet for the entire universe.
It is. It takes chaos and gives it order.
So to bring it all home, we started with that copper pot and silver ring.
And realized they're chemical siblings because they live in the same neighborhood, group 11 on the table.
We learned that the atoms that make them up are mostly empty space, and what we feel as solid is just force fields.
And we saw how the electron handshake determines everything, whether a metal bends or breaks, conducts or insulates us.
It really does change how you see the world. I don't see a table anymore. I see this buzzing cloud of repelling forces.
And that leads to, I think, a final thought for you to take away.
Let's hear it.
We tend to look at the periodic table as a historical document, a list of things we found, but I think you should see it the way Mendeleev did, as a map of what's possible.
How so?
We have these 118 Lego bricks. We know the rules for how they click together, but we have only built a tiny, tiny fraction of the structures that are theoretically possible.
So there are combinations of atoms we've never even tried to make.
Trillions of them. New materials, new medicines, new technologies. They aren't magic. They're just arrangements of the atoms on that table that we haven't figured out how to build yet.
The ingredients are all right there. We just need to find the recipe.
Exactly. The periodic table isn't a finished story. It's an invitation.
I love that. So keep your eyes open. That copper coin, that neon sign, you're looking at the fundamental ingredients of everything. Thanks for diving deep with us.
Always a pleasure.
We'll catch you in the next one.